In a moment, I'll be going on into sunrise On Forever. This is by Mary Lloyd. Let's see. Too fast.
Hello, we have an in-house question for you. Uh, we need another person on the crew up here to set up and get the sound system and the computer going. If anybody's interested, note.
get to a stopping point?
Okay. If you need me to stop, you can do it now.
Well, thank you again so much. We really do appreciate it.
Thank you.
And it's always fun to hear the harp starting off our evening.
Oh, thank you. Were you able to hear me okay?
Well, we could hear you. I'm sure our sound system was not as good as some others, but at least we had the feel for it.
Oh, very good. I'm sorry, but I promise by next month I should have original sound. It'll be even better.
Great. We're looking forward to it.
Thank
Well,
you so much.
Thanks again.
Happy Friday
Yeah.
the 13th.
Happy. Yeah, and welcome everybody to the Friday the 13th June meeting of the Orange County Astronomers. We've got, as usual, a great program planned. And I guess many of us are probably looking forward to the summer solstice next week, because that means that our nights will start getting longer again, even though the days will be getting hotter. Anyway, I think without more ado, I will turn this over to Kyle for our club announcements, and then we can get on with our What's Up and with our speaker. Kyle, take it away.
Perfect. Yeah. All right, so welcome new members. Your name badges should be available on the whiteboard. If they're not, if you don't pick them up in the next couple months, they'll automatically be mailed to your home address. For those in person, coffee, donuts, and water are available up at the library entrance. The next ANSYS Star Party will be June 28th. And note that the Starbecue will be happening on July 26th. Astrophysics Special Interest Group will be meeting June 20th at Orange Coast College. You can see the building and room there. Beginners class will be meeting outside the planetarium on July 7th at 7:30. And the next board meeting is July 13th at 11:30 online. The trip Doug Millar.
Kyle,
yeah.
Just one thing about the ANSYS Star Parties. I believe this month we actually have 2 ANSYS Star Parties, which would be the weekend. I think it's the 21st, as well as the following Saturday, because new moon is Wednesday. Just wanted to let people know, and we look forward to seeing you all out at ANZA.
Awesome. Doug Millar's trip that he runs with Cecilia up to the Owens Valley Radio Observatory will be happening next weekend, the weekend of June 21st. There will be a star party that Friday evening, June 20th, and then the science program and star party will be on June 21st. If you are interested in attending, please contact Doug Millar. The entire program is free. You just need to get yourself up there and provide, have accommodations for yourself. I believe you can camp at the site if you would like. Doug, do you want to say anything else?
Yeah, there was some intimation that the dinner in Bishop would also be free because of the observatory. I can't tell you what they told me, but we're not going to pay for your dinner in Bishop. But the people who own the Starlight Motel, bless their hearts, have invited us to the motel on Friday night at 6 o'clock for an Indian vegetarian dinner. And on them, it's free. So if you're up there on Friday, we will all troop out except for one person. I'm looking for somebody who doesn't like Indian food, so they can stay at the site and watch the telescopes. Or not, who knows? This is about our 23rd year of doing this, and we've always had a good time because it's just unbelievable to go to a site like that and have carte blanche. What do you want to do? What do you want to know about? And with some exceptions, I went by one dish. It was about 2-foot dish with a wideband feed on it. And I said, Mark, what's that one for? He goes, oh, I don't know. Yeah, he doesn't know, right? It's a TLA dish. 3-letter acronym, anyway. He couldn't say what it was. Okay, so the 40-meter dish we get to climb up around in. We don't get to transmit. And by the way, don't bring your handy talkies or transmitters onto the site. They get real perturbed when it shows up on a trace for somebody's PhD. Yeah, you don't want to do that. And then Sunday morning, we go up to Bishop again for a bunch of us go to Jake's? Jim's. Up to Bishop for breakfast, and then you're on your own. It's a nice drive. There's lots to do. Lots of historical stuff. It will be 100, almost 100 up there. So bring a neckerchief with you and twirl it up, soak it in water, put it around your neck, and you'll be better. But be aware it's going to be hot up there. And just be glad we're not going to have this in Inyokern. At 4 o'clock is bug time. I'll be doling out smears of DEET so that you don't get bit by mosquitoes. I think that's about all. We're looking forward to it. We'll probably have about 30 people there from all over the place. Radio hams, astronomers, teachers, kids, whatnot. It should be interesting. And I'm going to tell you why we don't wear badges. But I'll tell you up there, not down here.
Thank you.
Okay, go ahead, Kyle.
Awesome. Thank you, Doug. Next thing on the agenda, the upcoming beginners class on July 7th that I mentioned earlier, meeting outside the planetarium, and it's the how to use your telescope class. So if you have a telescope and need some help learning how to either set it up, use it, any of the above, please come on out. It's a great resource for all our club members. As I mentioned, the Starbecue will be July 26th. The beginners class on August 1st will be basics of astrophotography. The Adopt Scope program is currently up and running. You can see here how to get to the information on the website about the program. There's also, as shown there, a sample adoption agreement and an inventory of the scopes available for adoption. Our outreach events coordinator is Martin Christensen. Please contact him if you are able to help with any of these upcoming outreach events. They're always a fun time, so please come on out and help if you are able and willing. Dave Fisher is the Serious Astronomer editor. If you have any items of interest.
Hey, Kyle.
Yeah.
Hang on a second. We need to do something here because Martin is in the audience. Please stand up and wave your hand or whatever, Martin, because it's important to identify him. Wave. Thank you. So if you want to help with the outreach events, there's the guy to talk to. And believe me, they're a lot of fun. I've done it, and it's just a hoot. Okay. All right. Back to you, Kyle. Sorry.
Cool. As I was saying, Dave Fisher is the Serious Astronomer editor. If you have any items of interest that you would like to maybe have featured in the newsletter, please reach out to him and he'll review those items and provide more information. Friendly reminder to all those using the ANSA site to make sure the ANSA house is locked and to close the gates of the site if you are the last one to leave the site on evening. Remember to help keep weeds clear around your pad, and if you can help around the observatory, ANSA house and other common areas, that would be very much appreciated to help prevent wildfires. The next general meeting will be on Friday, July 11th, and the WhatsApp presentation is next. Thank you.
Our What's Up tonight is going to be done by Michael Michael Beckage. I can't read my own handwriting. And he is one of our own OCA members and would really love some feedback. And we're looking forward to this. So here's the mic.
Well, thanks a lot. Really great to be here. Reza reached out to me a couple months ago and said, would I like to give this a try? I joined the OCA as a lifetime member, probably 30 years. And, but I haven't actually been at an in-person meeting since pre-COVID. So that's why you haven't seen me. I've been out there in the online world. But I'm really excited to be here and give this a try. Last night, I know I'm supposed to take 15 minutes, so I'm taking note here. And yeah, let's go back. Here we go. There we go. I'm supposed to take 15 minutes. I did a dry run on this with my wife last night and took 15 minutes and 10 seconds. So we'll see how it works out. She liked it, but if whether you like it or not, my email address is michael@discoverthestars.net. And I welcome any feedback, good or bad, on the way we do these things. So welcome to summer, and I'm happy to be here tonight. So
if I may interrupt for a second, Sam, we see the presenter's view. Yeah, if you could.
Aha. How's that?
There we go.
I like that. I like that big view. So I think we're all aware that the sun follows a different path across the sky between the winter and the summer, and the winter and summer solstice. And that's simply because of the fact that as we go around the sun, in our elliptical orbit, at this time of the year, specifically the summer solstice, which is a specific moment in time, June 20th at 7:42 local time, the northern hemisphere is most directly pointed at the sun. What is not completely intuitive to people is the fact that the Earth changes distance from the sun, and on July 2nd, we're actually at the furthest point from the sun, aphelion, as opposed to perihelion. And if you do the math, which I did, it's covered by the picture there. If you do the math, we get about 7% less luminosity and intensity from the sun based on the inverse square law. Now, that's what tends to make the northern hemisphere a little bit milder climate than the southern hemisphere. Now, to call this some of the facts here, will it ever get dark? On the solstice, sunrise is at 5:42, sets at 8:08. We have 14 hours, 26 minutes with the sun above the horizon, less than 7 hours of real darkness if you add in, dawn and dusk. And so I got to tell you, the older I get, I really like stargazing at 7 or 8 o'clock in the evening. And that just ain't going to happen right now. By the time it really gets dark, it's 9:30 or 10 o'clock at night. So you got to stay up. That's just the way it is. Now, let's talk about moon phases for a second. We just passed our full moon, which was known as the strawberry moon for harvesting time of strawberries. We got third quarter coming up on the 18th, new moon on the 25th, July 2nd, first quarter, and then back to a full moon in early July. Now, one of the things I plan my observing is I think about when are the best dark sky observing times, and then when is the best time if you want to plan a gathering, maybe have your friends over and have a nice moon that's not any planets or up. Got it. Okay. And so the best dark sky observing times are really centered on the new moon. And, June 17th to 27th, number one, the moon rises after midnight on June 17th. It sets by 10:30 on the 27th. And if you're going to have those gatherings and look at the moon and other cool things, then the window's from about June 28th to July 5th. Perfect for July 4th weekend and your holiday parties. All right, so let's talk for Earth-Moon system and the weird orbital mechanics that go on. You might have heard about what's called the major lunar standstill, and the strawberry moon is rising as far south as it pretty much will ever get. And that has to do with the odd orbital mechanics that we have. The Earth, of course, goes around the sun in its orbit, in what we call the ecliptic. And then the moon actually doesn't orbit over the equator of the Earth. It orbits slightly offset from the ecliptic plane that the Earth goes around the sun. So when you take the 23.5-degree tilt of the Earth, the ecliptic, and the inclination of the moon's orbit, which is also elliptical, you get these weird orbital dynamics that cause things like standstills. And what that does is based on all of the combined forces and the orbital mechanics, that inclined orbit of the moon actually rotates very slowly in an 18.6-year cycle. And we're kind of in the middle. We are definitely in the middle of that cycle where we have the most offset moon rises that you're ever going to see. And so the strawberry moon that rose, for those who didn't have clouds the other day, was even further south than as far as the sun ever gets at the winter solstice, which is pretty cool. It's not really super intuitive how all that works, but if you look at all those orbital inclinations, it all adds up. Okay, let's talk about the moon. I love the moon. And one of the first things you see on the moon when it comes out of being a new moon, when it's a nice thin crescent, is you'll see the mare. They stand out, naked eye views. You can see the darker spots. They're seas in Latin, right? Because people before telescopes thought they were lakes or oceans. Mare Crisium is a really nice, it's almost perfectly round on the limb of the moon. The first mare you really see. Interesting, it's about 2.3 arc minutes in diameter. And I find that at twilight, I can just barely see that with my naked eye view. So it kind of calibrates me what kind of angular resolution I can get with my eye. One of the cool things about Mare Crisium is it's right next to Mare Tranquillitatis, the Sea of Tranquility. And if you're trying to point out to people where the Apollo 11 astronauts landed, it's like a guidepost to something that people really want to know. Okay, Mare Crisium is also a really cool thing because right next to it is what I call my favorite crater. I looked at the moon for 40 years before I discovered Protlus. And, you know, I think I read about it in an article in Sky and Telescope or Astronomy, but it's a very fascinating crater because it's relatively young, it's bright, and it has this asymmetric ray pattern. And if you use a little bit of a magnification, it really is a great geology lesson that you can tell people. There are a couple of different theories as to why the ray pattern is so asymmetric, but it's thought to be maybe a very shallow impact. There's some geology around the impact site that shielded some of the spray or the rays from the impact. So anyway, I just want to say that this period, it's going to be best seen June 28th to July 5th. Okay, let's talk about planet visibility. It's pretty slim pickings right now. If you look at this chart, this actually depicts the blue is daylight, the black is dark. And about the only planet that's actually high overhead at all, especially later in this period, is going to be the planet Saturn. You get a little bit of Mars in the evening, but Mars is, of course, really, really small right now. And most of the action is going to be in the morning. One of the things that we can have fun with in the evening is between June, just coming up, June 14th and 18th, Mars is going to slowly glide past the brightest star of Leo the Lion, Regulus. And I think that is going to be one of the highlights of the month. I'm going to be watching. Mars is orange, magnitude 1.5 right now. It's only about 5 arc seconds in diameter, so you're not going to see a lot of detail through a telescope. But it will be right next to Regulus, which is blue-white, magnitude 1.35, almost the same brightness. And I think that the color contrast between Mars and Regulus on probably the 16th or the 17th, when they're only a degree apart, is going to be one of the highlights of the month. So keep an eye on that. Okay, let's talk about the morning sky. Here we see on the solstice, there'll be a nice grouping of Venus with a waxing crescent moon pointing the way to Saturn. Uranus is going to be too much in the glare to really do much with it. Then on the morning of June 22nd, we have a nice conjunction with the moon, Venus. It'll be in the same proximity as the Pleiades, and then Saturn way up high. So I think that's one of the dates to remember. Okay, where is Jupiter? Where's Jupiter gone? People always ask that at star parties. Well, Jupiter emerges from the sun's glare finally around July 10th or 11th. So if you're looking right before sunup, you might catch a glimpse of Jupiter. It's going to climb higher and higher in the sky as the Earth orbits the sun. And we'll get back to a nice, in a few months, we'll get back to being able to show people Jupiter and Saturn during an evening event. All right, so I wanted to throw out a suggestion. This is my take on this what's up. So one of the things that I've learned over the years is that most of us who live in a Bortle 6 or 7 sky, you can look up the Bortle scale if you're not quite sure what that is, live with a lot of sky glow. And if you really want to impress people and yourself with views through a telescope, one of the guides I use is called Binocular Highlights by Gary Saronic. And what I found is if a binocular object is good enough to tell people about, then it probably looks really good in a small telescope or a moderate-sized telescope. And so I use binocular highlights a lot for urban stargazing. Really great. You can see my stargazer's diary there along with my heavily marked up binocular highlights. It's also points away to some of the things I wouldn't think to look at. So here's some of my deep sky picks for the month. Number one, we can always point out the summer triangle of Deneb, Altair, and Vega. We can always tell people about arcing to Arcturus and spiking to Spica off the handle of the Big Dipper Alcade. But then Albireo up in dead center in the summer triangle, the end of this Northern Cross, the nose of Cygnus. Fantastic. And I got some images. Is there any way you can move the folks over or change the view? Yeah. Here. There we go. That's fine. There you go. So I just want to point, these are what I call the old favorites, right? We're coming back around again, thankfully, in the summer sky. We've got number one, Albireo, beautiful double star. Oh, now I'm not advancing. Uh-oh. Okay, great. There we go. And then high overhead, along with Arcturus, we got Hercules and Messier 13, right? Over off at the boundary between Aquila and Scutum, we've got Messier 11, one of the best open star clusters in the sky this time of year. And then finally, some of the most high surface brightness planetary nebulae, M57 and M27. So these are the old favorites that are now coming into view. Fantastic. There we go. And then what I'm going to call extras, if you've got like a computerized digitizing telescope, you might be able to image M51, or otherwise you pretty much need to be in a dark sky to see the famous Whirlpool galaxy. And one of the objects I discovered through binocular highlights was Omicron 1 Cygni, which is a beautiful multiple star system not too far from Deneb in Cygnus. And Omicron 1 Cygni is comprised of a white star, an orangish or reddish star, and a bluish star. So some people call it the patriotic multiple star. Very cool object if you haven't looked at it. And finally, what the heck is going on with T Corona Borealis? You've heard last year, oh, it's gonna blaze, it's gonna nova before the end of 2024. It still hasn't yet. Perfect time. Basically, every clear night, I went out and looked. It's right next to Hercules, easy to find. That's the location there, and we're looking for a star to appear where there's currently a 10th magnitude completely invisible star. So my advice, every night, it's clear. Go out and look. Is it there? In case you miss it in the news. All right, let's talk about dates to remember. June 14th through 18th, Mars glides by Regulus within 1 degree. I think that's going to be something you don't want to miss. Third quarter moon near Saturn in the morning sky on the 19th. Summer solstice on the 20th. June 22nd, a very nice conjunction. Worth getting up for, in my opinion. Got to get up about 4:30 if you really want to miss the solar glare. On June 29th, we've got Mars less than 2 degrees from a waxing crescent moon with Regulus nearby. It would be beautiful. Mercury. I didn't say much about Mercury because it's always kind of tricky, but it is at greatest evening elongation, Eastern elongation on July 4th. So give or take a couple days, July 2nd, July 4th, 5th, 6th. It is a full 26 degrees from the sun. It's magnitude +5. It is 5.2 arc seconds in diameter, which is as big as Mars, and it's 39% illuminated around that time. And so if you have any kind of decent seeing or maybe go to scope and find it before it's dark, you might actually see the crescent of Mercury, which I've only seen a few times, and it's pretty cool. And July 4th or 5th doesn't get any better for a holiday party and impressing your friends and relatives with what you can do with your telescope. So that's my take on what's up. And here I am at a dark sky site with my old C14. Feel free to contact me if you like. Thank you.
Thank you very much, Mike, for a great presentation. You covered everything and every taste. That was great. Thank you very much. And looking forward to have you do more of these in the future. So without any further ado, let me go into introducing our speaker tonight. Our speaker tonight earned her PhD in astrophysics from the Sorbonne Paris Cité and pursued postdoctoral research at UCLA. She was an inaugural year Keck visiting scholar at Keck Observatory and continues at UCLA as an assistant researcher and adjunct assistant professor in the Galactic Center Group. Please join me in welcoming Anna Ciurlo. Anna.
Hi, everyone. Do you see my screen?
Yes, we see your screen full. Great.
Great. All right. Thank you very much. Thanks for the invitation. I'm very happy to be here. It was very interesting to hear all these things happening in our skies. I wasn't even aware of all those things, so I will make sure to look out for these. So thank you. Okay, let's get into this. What I'd like to do today is take you to a trip to the center of our galaxy. That's what I study, but along the way, I just want to talk about our galaxy a little bit. Before I started, I just wanted to give you a few words on my journey toward astronomy. The nice introduction gave you an overview, but if you gather a little accent, that's because I am Italian of origin. I went to France to study astrophysics, and I did my PhD there, and then I flew across the world to Los Angeles to keep on working with the Galactic Center Group. It's one of the best, if not the best, world group in the world to study this type of astrophysics. And I had the great chance to travel to Hawaii, not only for this collaboration, but very often to observe at the Keck Observatory there. And I was having so much fun that I'm still here as a researcher and adjunct assistant professor. So let's start talking about the Milky Way. So everyone here is very familiar with the night sky, but just to make sure, we're talking about the Milky Way. Usually it's just the visible part of our own galaxy, the Milky Way. That's what it looks like with a picture in a night sky. And it's this white band that is the result of the combined light of billions of stars, and it's partly covered by clouds, and it's called the Milky Way because of its white color. All right, so this is the visible part of the Milky Way. We cannot really travel outside of our own galaxy because it would be too far. But we can use other galaxies that we can observe in the sky to have an idea of what our own galaxy would look like if we could travel outside of it. So this, what we see, is another galaxy that, like our own, is seen edge on. So we only see the Milky Way as the band in the sky because we're right in the middle of it. But if we could travel outside and look at it from above, what we will see is something like the image on the bottom. So our galaxy is what is called a spiral galaxy. It's a disk with spiral arms. And the solar system is somewhere toward the periphery of this disk. And when we look the Milky Way in the night sky, we are looking through the disk of the galaxy. And this is the view that we will have from above. All right, so basically our own galaxy, it's a disk. It's referred to sometimes as a pancake, but as an Italian person, I prefer to think about it as a pizza. And to give you an idea of the size of this, if you think about a grain of salt on this pizza, in just one grain of salt, you could fit the entire solar system about 100 times. In real hard numbers, what does it mean? Well, the diameter of our own galaxy is 100,000 light years. And just as a reminder, 1 light year is about 5,880 million miles. So where are we? Right here, 26,000 light years from the center, which means that when you look at the light from the Milky Way in the sky, you look at the light that started from the very center of the galaxy 26,000 light years ago. That's roughly corresponds to when we were doing paintings in caves. So we were around, but it was a while ago. All right, so what is a galaxy? A galaxy, you can think about it as a city of stars. Stars don't live alone in the universe. They're not scattered uniformly across the universe, but they gather in and they cluster into galaxies. So our own galaxy, the Milky Way, it's also a city of stars. And so let's look at the map of our own city. There are different neighborhoods. For example, there is the disk of the galaxy. That's where we live. This kind of neighborhood can be imagined as the residential areas of a city. So it's a very quiet neighborhood. It's quite boring, not much is happening, but that's kind of nice for us because it's pretty safe. But there are other sites within the disk of the galaxy that you can think about as the industrial neighborhood of the city, where stars are formed. You see an example here in the Orion Nebula, or where stars are destroyed. You see here an example with the Crab Nebula. Then another neighborhood is represented by the halo of the galaxy, where we find globular clusters. This represents the historical neighborhood of the galaxy because this is where we find some of the oldest stars in the whole galaxy. And as any historical place, they can tell us about the history of our own city of stars. But now, the part that I'm really interested into and where I want to start zooming in is the center of the galaxy, which starts with the bulge. This is the downtown of our own city of stars. It's a place that is very crowded. It's very busy, a little dangerous, but extremely interesting. So let's get closer to this. First of all, let's see if we are thinking about the Milky Way as a city. We looked at the map, but now we need exact directions of where to go there. And I know the people here care a lot about how to look for things in the night sky. So in case you don't know how to find the center of the galaxy, well, it's supposed to be the brightest spot in the Milky Way, but it's kind of hard to see it with the naked eye. So one good way to finding it is finding the constellation of the Sagittarius. You can actually either find the Sagittarius of the Scorpius, but I find the Sagittarius very easy to spot. And people say the Sagittarius kind of looks like a teapot, and the point of the teapot points to this kind of triangle here, and the galactic center is right here. So next time you look at the Milky Way, you can find the galactic center yourself. All right, so now we know where to look in this much higher resolution and much longer exposure images. That is very nice. The galactic center is right here. So we know where to look, but what do we see? Not much, actually, because most of the light, as you can see, is blocked by the dust clouds. So what do? Well, we know that this picture is taken in visible light, which means the light at which our eyes are sensible, but we know that we can actually take pictures in other colors, in other what's called wavelengths, to try to see through the clouds. So the typical wavelengths or colors at which we want to look at are radio or infrared or X-rays. And of course, depending which part of the spectrum of light we're looking into, we're going to learn something different about what we're interested in. For example, this is a nebula seen in the visible. It's a very pretty image. You see these big pillars, but you don't see many stars. What what if you want to see what's behind these pillars? Well, you can take a picture, for example, in the infrared. Now, there is still a little bit of gas, but you see many, many more stars appear, and you can really peer through the veil of this dust and gas. Or, for example, you can also look at the X-rays. You see only a few stars, the most energetic one that can trace some of the interesting processes going on. So let's go back to this image of the Milky Way galaxy. This is in the visible, but now let's take the same picture exactly at the same scale, but in the infrared. And here is what you get. You see appearing many, many more stars, and now actually finding the Sagittarius constellation is basically impossible. There are just too many stars, but finding the center of the galaxy becomes pretty easy. It's right here, and you can tell it's the brightest spot of them all. Why is that bright? Because there are many, many stars there. So let's start zooming in. This is an image taken by the Hubble Space Telescope, where I kind of tuned down the luminosity only to show you the brightest stars of them all. There are lots of stars in an area of about this radius. This corresponds to the distance between the Sun and Proxima Centauri, the closest star to us. So in that same volume nearby the solar system, there is just one star, right? The Sun. But if you take the same volume in this image, you have actually 1 million stars, to give you an idea of how dense this environment is. And the center of the galaxy, the very center, is right there. So since it's so crowded, it's very hard to observe it. We need to use very big and very powerful telescopes. Namely, what I mainly use is the Keck observatories on the top of the Mauna Kea Mountains in Hawaii. You can kind of see them here up on the mountain. And this is the headquarters of the Keck Observatory. Here is a zoom in of the telescopes. It's twin telescopes with 10-meter diameters each and lots of very cool instruments on top of them. This is a picture of me and a colleague observing at the headquarters in real time, the center of the galaxy. And then this is me doing the same thing, but during COVID, where we couldn't travel to Hawaii to do this, unfortunately. Just to give you an idea of the size of this telescope. So here you see the dome of the Keck telescope. So this is the mirror. And if you see it here, tiny, tiny, that's an astronomer next to this very big mirror. But maybe this is a better picture. So this is the size of the mirror at one of the two Keck telescopes, and that's the size of me right next to it. I'm not very tall, but still you can tell how big this beast is. All right, so big telescopes are great because when you have a larger collecting area, you get more photons, you can see dimmer things, you can see actually much more in detail, you can separate objects. But the problem is that this very big telescope sits on Earth, and so you have to observe through the atmosphere. And the atmosphere, it's very useful, of course, because that's what allows us to live on Earth, but it's very annoying for astronomers using big telescopes because it introduces blurring. Especially, the problem is the turbulence in the atmosphere that introduces blurring of your objects, and so smears out and basically destroy the power of your very big telescope. So in order to really be able to use big telescope, you need to use different techniques. And what I'm showing here, it's what's called adaptive optics. It's a technique that allows you to correct for the blurring of the atmosphere in real time. And the way you do it is using lasers. So this is a real image of the twin telescopes of Keck with lasers pointing both at the center of the galaxy during one night of observing a few years ago. So how does this technique work? In case you don't know, so there is a laser that is basically a fake star that's pointed at the atmosphere, and you observe this fake star in order to study in real time what is the blurring that is introduced by the atmosphere itself. So basically, the blurring of the atmosphere deforms the image of your star. So that basically what's called the wavefront looks like chips. But you can look at those chips and basically you can feed back the shape of these chips to a deformable mirror that compensate exactly for that deformation. And instead of having chips, you see your chips become pancakes. So you have corrected for the deformation and the blurring of the atmosphere. This is what you get if you observe a star without adaptive optics with a very big telescope. But when you close the loops on this technique, the adaptive optics, you restore a point-like source. So this is very powerful just to show you, this is what happens at the center of the galaxy. These are all stars. You cannot see them, but it's a little blurry. And we're very interested in this very tiny area here, where you basically don't see anything if you don't use adaptive optics. But if you switch on adaptive optics, that's what you get. You can actually see stars you were not able to disentangle at all without adaptive optics. All right, so let's go back to this Hubble space image. Now, thanks to KEC and thanks to adaptive optics, we can zoom in even more. So let's take this little area and let's blow it up. There it is. So we can take pictures of the center of the galaxy, and not only we can take pictures, but we take repeated pictures, and we've been doing this in the past almost 30 years. So you can see how the stars that you have all over the place here, these are all stars, how they move throughout the years. And now I'm going to show you this animation that shows exactly that. So not all the images look the same because they are not all of the same quality and depth, but you can see that every single point that you try to follow in this image, it's moving. Every single star, it's moving. And if you look at the stars closest to the center of the image, in particular, this star of which I'm tracing the path is making a full orbit around one point. So what's in that point? There is no star. We don't see anything in there. Well, we can know what is in that point thanks to gravity. So gravity is what makes everything stick on Earth, but also what keeps the moon orbiting the Earth and the moon orbiting the sun, and ultimately the solar system orbiting the galaxy as well. So when you look at how things orbit, you have information on the mass around which they are orbiting. So thanks to the motion of that star that I showed you before, we figure out what kind of mass was required to have the star orbiting. And we measured that you basically need 4 million times the mass of the sun. And that gigantic mass is not only very big, but it's concentrated in a relatively small volume. That's basically the equivalent of taking 4 million suns and sticking them inside the orbit of Mercury. So it's a lot of matter. It's an object that is extremely dense, so dense that it can only be a supermassive black hole. And this is exactly how it was demonstrated that there is a supermassive black hole at the center of the galaxy, which granted the Nobel Prize in Physics in 2020. So here you have a rendering of the orbits of stars. So this is in yellow the star I was talking about. It's called SO2, and this is the position where this supermassive black hole lives. Not only we were able to show and demonstrate the existence of a supermassive black hole for the first time, but sometimes stars come so close that you can actually measure the bending of the space-time due to the presence of the supermassive black hole. That's what we did in 2018 when the star SO2 came so close to the supermassive black hole that its orbit shifted to what you would have expected only based on Keplerian motion. And we detected what's called the gravitational redshift of SO2, and so we're able to test general relativity nearby supermassive black hole. All right, so far I only talked about taking images, but there is another tool that is extremely important here, that is spectroscopy. For those that don't know it already, when you pass the light coming from a light source through a prism, what you obtain is basically a rainbow. That's the exact same effect that produces rainbows in the sky. But not only that, so when you pass the light through a prism, you have what's called a continuum of light. But if, for example, you have a cloud in front of your emitting source, that's going to absorb part of the light, which creates some absorption features. Or on the contrary, if you have a cloud that is heated by a light source, then you're going to have emission lines. So a spectrum is basically a combination of a continuum and emission and absorption lines. And we describe that as the intensity of the light as a function of wavelength. So it's a function of color also. So this is just a rendering. What I'm showing here is a real spectrum at the center of the galaxy. And the powerful thing is that when you take spectroscopy data, you can look at different components. For example, if you look at absorption lines, very often these are produced by the photosphere of stars. And so looking at absorption lines tells you about the stars. But on the other hand, there are also emission lines, and this mostly we saw come from gas that is heated and emits light. So you can look also at the interstellar medium. And as you can see, this is the same image, but looking at the stars or at the interstellar medium, you can have a very different picture of the different emitters in the area. Let me focus now on the interstellar medium, which is my specialty. So I talked about taking images or doing imaging, and also taking spectra or doing spectroscopy. But there is another thing you can do, which is combining the two, which is called imaging spectroscopy. In this case, if you have an image, for each pixel of your image, you also measure a spectrum. So what you end up having is a data cube, where every single pixel has also a spectrum. So you have two spatial dimensions and one wavelength dimension. So here you have a rendering on the left, and on the right, a real data taken at the center of the galaxy. So this data cube, you can think about it as a cake, and you can slice your cake in different ways. You can slice it around a wavelength chunk. For example, if you're interested in looking at the gas, you want to look at emission lines, and you can cut a chunk of your cake around a specific emission line you're interested in. Now, again, as in the case of the imaging data, we also have this imaging spectroscopy data for many, many years at the center of the galaxy, so we can see how gas features evolve with time. So in this case, I sliced a chunk of my cake, and I'm looking at this emission line. They look like these little blobs in emission lines, and I can track them and see how they move with time. So here you see the circle shows the position of each of these three features in 2006. This is the black hole at the center of our galaxy, and you see that they are all moving. This guy is coming this way, this guy is going this way, and this one is also moving this way. But this is a cake. I can slice it however I want. I can slice it also the other way. So I can take a chunk, for example, I can focus on one of these interesting blobs, and I can cut a chunk in the opposite direction along the wavelength axis, and so extract the spectrum of this object. Again, I can do this for many, many years, because we have years and years of data, about 15, 20 years of data now. And so I can see how its spectrum, how its emission line evolve with time. And what I see is that the emission line from this gas, it's moving, which means that the object is moving along the line of sight. And what we see here is caused by the Doppler effect. So if you put these things together, you can basically measure the orbits of all these objects. And so we found two interesting things. We found objects that look like gas clumps, but we also measure the objects, the orbits of these objects, and we saw them evolving with time. So what does it mean? The first time we saw these objects, the first one of this object, people thought this was just a gas cloud that was going to be destroyed because it was going to pass very close to the supermassive black hole, and a pure gas cloud is not supposed to be able to resist the extremely strong tidal forces of the black hole. So here is a simulation of what people expected would happen to one of these clumps coming very close to the black hole. Is this one in red? It was expected to get stretched and then just completely disrupted. But that didn't happen. This cloud actually survived. Here, this is the position of the supermassive black hole. These are real observations of this cloud. You see it here. This is in 2011, more or less, when it was discovered. And then this animation shows you in 2012, 15, 17, and it basically goes around the black hole and then shows up on the other side, and it got maybe a little stretch here and there, but it's still there, it's still compact, it survived. And that's very puzzling, because people thought these were just gas clouds. Then we discovered many more of them, and so it's not likely to see those many clumps of gas just hanging around, staying compact and surviving the black hole. So we actually think that there is something massive that is keeping these objects together and basically saving it from being destroyed in the case of this very close passage, and in general it's just keeping it compact throughout their story. We saw in the animation before that even the other ones that didn't come that close, they still anyways stay pretty compact. So we believe there is a star that is hidden inside. It's rendered here in this. This is not a real image, it's just a rendering. This is the black hole, and then you have a star hidden by dust, shown here in red, and then surrounded by a gas shell. That's what we actually saw in the data I showed you previously. So these basically look like very puffed up stars. which is fine. That explains why they look like gas cloud, but they behave like stars, basically. But stars don't usually look like that. So the question is, how do you end up having these puffed up stars? What can create it? So for discussing this, I want to do a step back and talk about the stars in the center of the galaxy. Spectroscopy allows us to study the gas, but also the stars, right? And when you look at the spectrum of a star, you can actually learn on its age, depending which kind of emission or absorption features they have. So here, for example, in orange, you have several of these are identified as old stars, and many are young and massive stars. And here is the black hole. Now, the thing is that, so we know there was some kind of formation event of stars not too far ago, because there are some young massive stars. And we know that very often stars are actually formed in pairs. So what are these binaries and what happens to them in this environment? So the interesting thing is that, so in the galaxy, more or less about 50% of stars are believed to be formed in pairs. So we expect more or less the same to be true also at the center of the galaxy, but the important thing is that you're very close to a supermassive black hole, and that does something to your pair of stars. So these two stars, this binary system, they are orbiting each other, and together they are orbiting around the black hole. But the presence of the black hole basically injects perturbations inside the motion of these two stars, so they don't just orbit around each other with the same orbit all the time. But basically, the black hole makes the ellipticity of the orbit of these two stars oscillate. So sometimes the two stars can actually get pretty close to each other. And if they're close enough, they can start stripping material one from the other. And if they do it enough, they can eventually merge. And this process is very messy. It sheds a lot of gas and material. So you end up with a new star that is the product of the two merged stars with around some dust and gas. So that's how you would potentially create an object that looks like these puffed up objects we discovered. So that's interesting, because it fits many ways, right? You know, you expect to have binary systems in the center of the galaxy, and you expect them to merge because of the presence of the black hole. And maybe that explains why these objects that look like gas and behave like stars actually stay compact. We call these objects G objects. You might have seen in the other slides are called G2, 3, 4, 5, and 6. Here in this pretty three-color image, you also see them. That's where the black hole is. Here, this red dot, this is G2, this is G3. You saw in all the animations, these remain very compact. So maybe that's because that star inside is keeping it like that. And this kind of differentiates them, in my opinion, to what happens to a real gas cloud. For example, we can look at this gas cloud called X7. This one, I think, looks much more like the simulation I showed you before, with a gas cloud being stretched and accreted onto the black hole. This object, we have been observing it for the past 20 years, and this animation shows you its evolution. So it starts a little elongated, but pretty compact, and then the tidal forces of the black hole stretch it. So it's also orbiting. So it's moving up. The black hole is right here, and the tidal forces of the black hole are stretching it. And its evolution is pretty dramatic, more than doubles in length. It gets much thinner. And in the future, we expect to start break up and ultimately be accreted onto the black hole. So this is very different from what happens in the case of the G objects, where they stay compact. This cloud is being basically spaghettified by the black hole itself. So how would you create that kind of gas cloud? There are many scenarios, but one interesting possibility is that you have an encounter between a red giant with a very puffy atmosphere that maybe gets an encounter with a compact object, for example, a stellar mass black hole that can eject some gas and then create this object. And it's interesting that one of the G objects has a motion that is pretty similar to this object, X7. So maybe the same phenomena that created G3 also ejected a little bit of its gas and put in a slightly different orbit at X7. But this is still under investigation. It's just a preliminary possible result. So there are many things that are interesting here. We want to learn how stars form and evolve nearby a black hole. We want to track how gas clouds interact with the tidal forces of the black hole. But also all of these things are very puffy, even though they have a star inside or not, but they all are pretty puffy and they come pretty close to the black hole. So they have the potential of bringing material onto the black hole, being accreted and enhancing its activity. And that might be what explains what we observed in 2019. We were at the telescope taking the usual images of the stars, the one that are used to produce the animation that shows all the motions of the stars I showed previously. And usually you don't see much of emission coming from the material immediately surrounding the black hole. It's pretty dim. But sometimes if a new material gets onto this surrounding area, the friction of this accretion process can produce a lot of light. And that's exactly what we saw. So usually the black hole, you basically barely see it. And that night we saw this bright, speaking bright. And this is just an animation showing you a couple of hours of observations. And in the span of only maybe 10 minutes, the black hole became the brightest we have ever seen in one night. And that's maybe us witnessing the black hole having a little snack, which is quite interesting. And of course, these are only some of the fun things you can study at the center of our own galaxies, but there are billions of other galaxies around the universe. Most of them are pretty far away, but the closest one to us will hopefully become accessible to us pretty soon. Well, how do we do that? Well, of course, we need even bigger telescopes. This is the size of the Keck telescope mirror compared to the size of a basketball field. It's pretty big. The other biggest telescope that exists of the same kind, let's say, not considering radio telescopes, is the Very Large Telescope in Chile. That is an 8-meter diameter telescope, and then there is another telescope in the Canary Islands. And as you remember from before, these are pretty big, and if you compare them with a basketball court, they are big. The other two important telescopes that we are using a lot is the Hubble Space Telescope, of which I showed you an image previously, and its successor, the James Webb Space Telescope, which is quite much bigger than the Hubble Space Telescopes at infrared, lots of infrared capability. But you can see this is smaller than Keck. But of course, the James Webb has the great advantage of not having to observe through the atmosphere, and so don't have to go all the trouble of using adaptive optics and so forth because it lives in space. So the sensitivity is incredible. So it's space and ground observatories are really complementary. But of course, the advantage of building on the ground is that you can make your telescope extremely big. So the next project that astronomers really would like to be made is the 30-meter telescope. As you can tell, the naming of telescopes by astronomers is not extremely original, but this is the mirror of the 30-meter telescope compared to everything else. It's really big. And not only this, the ideal would be to build this in Hawaii, and right next to Keck on the top of the Mauna Kea mountain. But also there is another telescope that is being built by the European Space Observatory that also takes care of the VLT in Chile as well, that is called the ELT, or Extremely Large Telescope. Again, not a very interesting name. And this is an even bigger telescope of almost 40 meters diameter. And to give you an idea of how huge these are, this is again me next to this huge mirrors. So Keck allowed us to do many things. We were able, with adaptive optics, to see stars as they orbit around the black hole. That what allows us to demonstrate that there is a supermassive black hole at all, testing general relativity and so forth. But with TMT and similar very large, extremely large telescopes, we're going to be able to do even more. So on the left, you have the area around the supermassive black hole at the center of the galaxy, and you see stars as they move, as they are observed by Keck. And on the right, you have the same exact area, the same scale, but what we will be able to see with the TMT. So as you can tell immediately, there are many more stars that become available because we can disentangle them much better. Stars that were kind of all melted together before now appear very clearly. And when you play a movie, imagining of taking images over and over again, the same way we do on the center of the galaxy, that's what you obtain. Oops. Oh, the video doesn't play. well, it doesn't matter. But basically, the thing is that you will be able to detect stars that are doing very small orbits around the black hole. And that's important because knowing how an orbit evolves with time tells you about the properties of the black hole. And so this is going to allow us to look into more details into the properties of the black hole itself. And if you think about this mysterious G objects, these puffy stars, we're going to be able to resolve them, see exactly how they are and how they evolve with time in a way that is not possible today. So in this very last slide, I want to show you this animation. This shows you the stars orbiting at the center of the galaxy. You have young stars and old stars. It's in green and orange. And in purple, you have these G objects. And this is an animation that shows you a flyby by the center of the galaxy. And as you can see, there is a disk of stars, and there are so many stars also that have more scattered orbits. The dynamics are complicated, and they are connected to how the stars were formed. So we believe there might be a connection between all these pieces of the puzzle, the stars, the black hole, these G objects. They might be all part of a same story. It tells us how black holes influence their environment, and also how the environment kind of fits back into the black hole by bringing material on top of it. So there is still many things we need to understand, but this region is extremely rich and really allows us to dive into many interesting physical questions. With that, I thank you very much for your attention, and I'm happy to take any question you might have.
Thank you very much for the wonderful talk and enlightenment of a very special region. Thank you very much. That was a great talk. Thoroughly enjoyed it. So now let me let the audience know that the floor is open for questions. For the online audience, please send in your questions in the Q&A section. And for the in-person audience, we'll get to you alternating between in-person and online. So let me start with the first question online. Can you determine size or location of the black holes based on tidal disruption event of each G object?
So actually, we know about the rough size of the black hole and location thanks to the stars. And that's a way more precise way of measuring it, because the stars are really point-like sources, and the objects I'm talking about, they're like little blobs, and they are actually a little harder to track than stars. So you could, in principle, by looking at how these objects orbit, do the same calculation, but you actually have a more precise measurement if you just use the stars.
Okay, great. Thank you. Barbara, let's switch to the in-person audience.
Questions? Who wants to be the first to, yes, sir. The question is, the picture that you're showing right now, what's the distance across that? Is it like 40 light years or something else?
This is roughly, it's probably a fifth of a parsec, more or less. So it's yeah, much smaller than a light year. It's probably 15 arc seconds. So yeah, I think it's roughly a fifth of a parsec. So it's really small. That's why we need really big telescope. This is the galactic center. Actually, it's interesting. It's a notion that is very personal. If you say galactic center, it could mean hundreds of parsecs, or it could mean 1 parsec or a tenth of a parsec. It depends who you ask. So for me in this region, it's more like a tenth, a fifth of a parsec. So it's really small. That's why you need these very, very big telescopes.
Thank you. Back to you, Raisa.
Sure. So what do we know about the back history of these stars and the binary system? So is it possible that they were formed in a distance and then moved towards the black hole, or were they formed in that region? What can you tell us about that?
Yeah, so there are many things. So we don't, for the stars that we see, okay, let's separate between stars and these G objects. The stars we know, for some of them, not all of them, but for many, if they're old or young. And the problem is that you're not supposed to be able to have young stars there, because it's supposedly very hard to create stars nearby a black hole. Because, you know, a star is formed with the collapse of a molecular cloud that usually has to be left alone to do its own process in a kind of a quiet environment, that it takes a while. So nearby a supermassive black hole, where the cloud will be just shredded and elongated and ultimately accreted, it seems very complicated to have young stars, but we do. So why are there young stars to begin with? It's kind of a puzzle. Then why do you have binaries? Well, binaries, when you have a population of stars forming binaries, but not all the binaries are stable. So you accept to have more binaries in a younger population, that some of them merge, especially nearby a black hole, but just in general, some of them just are too far away or too close to each other. So it's not all of them are stable, basically. So it is possible that some of these binaries are part of the old star population and they were formed far away and then migrated inward. But for the ones that are, most of them expected to be part of the younger part of the population, it's still kind of a mystery to understand how they got there. There is some theory that showed you might be able to rejuvenate the stars. If you take two stars older and you merge them in a new one, the ratio of elements might make it look younger, but it's not clear if you would be able to rejuvenate enough, because we're talking about billion stars. These are the old stars versus millions of years stars, which is the younger one. So it's not clear if you can do it that much. So it's kind of an open question.
Okay, great. Thank you. Back to you, Barbara.
Okay, next question. Thought I saw a hand. Mike? The question was, are you converging on an accepted number for the mass of the supermassive black hole?
Yeah, the mass of the black hole is pretty well established now. So it's roughly 4 million times the mass of the sun. There's been a bit of back and forth, but now it's been a few decades that is more stable. The last measurements were done when the star went very close to the supermassive black hole. And one of the parameters you can fit when you try to measure this gravitational redshift I talked about is also the mass of the black hole. And it seems that independent measurement now agree on, I think it's 4.1. That's the latest number on the 4.1 million solar masses. That's the latest.
Other questions? Am I missing a hand? The question is, are they able to measure a wobble in the black hole from the stars going around it, or is it so massive that it doesn't wobble?
What sense of wobble in the position of the black hole? Is that the question?
I think that's what they were asking, yes.
So we won't, because first of all, we are not always able to detect the black hole itself. So just to be clear, we actually don't see the black hole itself, right? Because, well, you don't see a black hole by definition. You cannot shine a light at a black hole because it absorbs all light. But what we usually say when we say we detect the black hole, we mean the material around it, so the very close accretion flow and accretion area around the black hole. So usually when we see light, it comes from that, not from the black hole, just to make sure that's clear. And that is usually pretty faint. So it's very hard. We try to measure its position and see if it moves around. If it moves around, it might not be because of the stars that orbit very close around it, but the combined effect of all the stars around it, plus maybe some spin effect and other things. But it's kind of hard. And the problem is that it's often not really easy to detect. So it's it's also a problem because everything in this field that you're looking at here moves. So it's very hard to point your references. So we have a very complex way of building what's called a reference frame, where we try to stitch up together stars we see here with stars, same stars we see in a bigger field, where there are other stars that we see in a bigger field that we actually know are not moving. So it's like a stitching together process that is very complicated, which makes it even harder to make sure if the black hole is doing little wobbles in space or not. So it's very, very hard.
Great, thank you. Other questions? Yes, sir.
So, do you have any of your observations done by observatories?
The question is, are any of your observations done by off-Earth observatories for the work that you're doing yourself?
Yes, the James Webb Space Telescope and the Hubble Space Telescope. So that image that I showed you, we use that to kind of ground ourselves and try to see what are the stars that are not moving. That's one use of that, but also studying the stellar population. And me in particular, I actually obtained observations at the James Webb Space Telescope about a year ago to look at the distribution of the interstellar medium at a slightly larger radius, where we have basically a torus of material of around 1 parsec that orbits the black hole that in this moment is kind of kept away. But one day we expect it to rejoin the black hole, fall into the black hole, and trigger a phase of much more enhanced activity. And one way to try to understand this is understanding the physical conditions of this gas. Is it stable? Is it gonna fall? Is it forming stars? So the James Webb Telescope allows us to see this gas in a way that is not possible off Earth, and we are studying actually currently right now.
Cool. That all sounds really difficult. Okay, other questions? I'm sorry, what was that? The question is, does the black hole spin or rotate that you're able to see?
We are not able to determine that so far. It's probably spins. How exactly is very hard to know right now. So there have been some claims here and there, but I think there is no strong evidence now to tell us how and if the black hole is spinning.
I'm sorry, was that a question, Martin? No. Okay. I think we're ready for your side again, Reza.
Yeah, sure. So is there an established orbital decay for this star based on mass or distance?
For the stars, not for the objects. Is that the question?
Yes, specifically the questioner has asked that, but if you want to explain, why don't you go ahead and tell us about both the stars and the G objects? So
yeah, so
do you have established?
Well, most of the
Yes, sorry, go ahead.
Will just keep on orbiting the way they do. We don't see any star so far that is potentially coming close enough to fall into the black hole and be annihilated. We hope to find some of these stars with the next generation of very large telescopes, but right now we cannot see close enough. The star that I showed you before, the one that basically allows us to prove the presence of the black hole, where we tested general relativity and so forth, to make its full orbit, it takes 16 years. So we are right now arriving at the moment where we have basically 2 rounds of the orbit. And what happens is that sometimes the orbits precess because of the presence of unseen mass and black hole parameters. It's complicated to disentangle the different effects, but it allows you to really try to track this kind of effects. But this star is not falling in, it's just moving very slightly, so it's hard to measure all these things and is not ultimately going to accrete into the black hole. Maybe when it passed close by, a little bit of it got detached and fell into the black hole, but it's not enough to be seen on the star itself. So we don't see any star that is eaten at the moment. For what concerns the G objects, I think the same is true. They are, well, basically most of them are not passing close enough. They're going to be completely destroyed if they have a star inside that kind of keeps them together. On the other hand, that elongated object X7 I talked about, I think that is going to die in the next 25 or 35 years. That's its expiration date, because it's just coming through, and you can already see in some of the most recent observations the tip of it slightly getting detached from the body, so it's just going to be pulled apart and destroyed. So it's not going to complete the full orbit, it's just going to be destroyed before it does the full orbit. I hope this answered the question.
Great, thank you. And the next question is about the telescope. So you did mention that the larger the telescope gets, it's better for your work, and you're looking forward to the larger telescopes to come online. So the questioner wants to know if there are any other technologies that you use, maybe the gravitational telescopes, LIGO and stuff, that would help you in your work.
Yeah, so LIGO is very different because it measures gravitational waves. So there is some interplay in the sense that basically LIGO, in order to measure a signal from gravitational waves, the signal has to be very important. So that's why we mostly see just like huge stars merging together, or even gigantic black holes, or even galaxies merging together. So it might be that when you actually detect binaries and you see them merge, especially in some cases where you have very massive ones, you can then produce gravitational waves that can be detected, maybe not by LIGO, by the next generation of interferometers in that way. But right now it's more of a preparatory interplays, not something we can really use right now, because basically when you use telescope, you're looking at the sky. But when you use interferometers like LIGO, you're basically hearing the sky. So you don't know exactly where your signal is coming from. And here we're very focused on one region where we need to see the details. So it's really two things that are hard to interlace in this moment. But we do use the Event Horizon Telescope, but it does use a different technique, let's say.
Yeah, so the questioner wants to know what other techniques beyond that you use. So you use the Event Horizon, and are there other technologies that would help you also?
Yeah, so the Event Horizon Telescope is not something I've used personally, but it's the whole collaboration that produces images, and they produce the first images of the area around the supermassive black hole at the center of our galaxy as well. So that's completely different, because it's a very different scale. You're looking much, much closer at the black hole, so you lose sight of the bigger picture, but that's how you can maybe try to measure the spin of the black hole, which type of black hole it is. The problem is that that kind of work is not necessarily model dependent, but it's very heavily dependent on a lot of models, because it's not just a picture, it's a reconstructed image using interferometry in a different ways. So it's a much more complicated than just a picture. So I think it absolutely needs to be used in conjunction with other techniques in order to make sure you're not getting it wrong.
Okay, great, thank you. Barbara, back to you.
Is that on? Yes. The question is that the pictures that are shown basically show the area of the black hole as empty, or nothing seems to be there. And the question is, why are we not seeing the accretion disk, or a brightness where the accretion disk would be?
Yeah, so that's a very good question. There are two things. First, it depends on the size of the accretion disk. If it's too small for us to have the resolution to see it, we might not see it. And it's not necessarily there. Maybe it's not really an accretion disk. Maybe it's more of an accretion flow. It's not organized in a disk, so it doesn't necessarily look like disk. But there has been claims of observations done in the radio wavelengths that claim the existence of an accretion disk around the black hole, a cold accretion disk, because people saw gas basically on the one side moving far away from us and the other side moving toward us, which seems to be the signature of a disk rotating around the galaxy, around the supermassive black hole. This was seen in the radio with the hydrogen recombination lines that are just hydrogen. So you would expect to have the same kind of structure also in the infrared, where actually the transition of the hydrogen are much more likely to happen than in the radio, but we don't. So it's very puzzling why the disk would be there and it's not seen in the infrared. So there's been a claim of the detection of an accretion disk. So some people said they saw it, but it hasn't been able, other people, actually, this was my study. I wasn't able to confirm it in the infrared, where it should be much easier to see it. So either that's a structure that is actually transient, so you have a disk, it's created, then it's dissipated, and it's created again, or something like that, or there is something else we quite don't understand yet. But we are not sure whether we have seen the accretion disk, if it's there at all, what's this structure and shape, but at any rate, it's going to be very small, even in these images, so it's hard to see. But we do see light coming from the area that varies with time, depending how the accretion onto the black hole is happening in that specific moment.
Yeah, it looks very intermittent from what you're showing us. Yeah. Are there other questions? Yes, sir, in the back. The question is, given the density of mass in that area, are there other black holes aside from the supermassive black hole in that area?
Okay, great question. Most likely, yes. It's hard to see them, of course, because they're going to be much smaller. People have been very interested in looking for not just any black hole, but intermediate mass black holes, which are a missing link in how we create supermassive black holes. People believe you create black holes. We know you can create black holes sometimes when a star dies, if the conditions are just right. But these black holes only have 1, 2, 5, 10 times the mass of the sun. How do you get from there to having millions or even billions of times the mass of the sun? And so people think that one way of doing it is in a hierarchical model, where you take two black holes of few times of the mass of the sun, you merge them together, then you merge them together, then you merge them together until you get to millions and billions. But then, if that is the case, you should observe a lot of black holes that are in between the 10, 20 solar masses and the millions and billions of solar masses, so hundreds of solar masses or thousands of solar masses. But even though there has been some claims, there is no strong evidence of any intermediate mass black hole. So people are very confused and have been very interested in looking for intermediate mass black holes in the center of the galaxy as well. You can imagine that black holes and massive stuff in generally have a tendency to naturally migrate toward the center. So we believe there is a vast population of regular black holes there for sure. And this intermediate black hole that has been claimed, but it's actually an intense debate, and people do not agree if we actually see intermediate black holes there at all, or in general in the universe itself. So it's still kind of a very open question.
Sounds like one we have to stay tuned for. Any other questions? Yes, sir. I believe that was what she was saying, was activity around the area of the black hole. The question was the bright spot that periodically shows up. He wanted a clearer explanation of what that actually was showing.
These are basically a time lapse. So one image taken after the other, you can see the timestamp here. So they are taking in the span of a couple of hours. And these are short exposures, only a few seconds each. And basically what you see is that, well, the stars, and you see kind of the full frame blinking a little bit because the quality is not always the same. There is a cloud passing by, the atmosphere is a little bit more turbulent at times, and these are short exposures. And then basically what you see in this area, this is where the black hole is. And usually you're barely able to detect the material around the black hole, but that night the material got extremely bright for a little bit of time. not very long. After a few minutes, this bright spot went away, but we saw it extremely bright. And we believe that's because this was an accretion event. So some material got pulled in, it joined the accretion flow, whatever that has a shape of a disk or not. And the friction of this material joining the accretion flow is what created this huge spike in luminosity while this material got accreted. Where this material is coming from is not clear. It could have been one of the objects, the one that survived. It came by pretty close, but maybe still was able to be stripped of a little bit of material, and that material made its way closer and closer to the black hole, and then it kind of fell into the closest accretion flow. Or maybe it was that star that came very close by that allowed us to measure the general relativity test that left a little bit of material. So this is just a little bit of matter falling onto the very inner more part of the accretion flow, and this is what most likely produces this light. Basically, we see the black hole emitting light in different ways all the time. This was extreme because it was really a huge spike in luminosity. You can see just it's very bright and then it gets dim again. But usually on a typical night, you see it getting a little brighter and then dim, 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 and then a little brighter. So it's much more like quiet, but there is variability. And that variability is observed at all wavelengths. This is in the infrared, but there is variability observed in the radio, there is variability observed in the X-rays, and there are different theories on where each of these light it comes from different areas within the region around the black hole. Some of them trust the innermost region, some of them trace slightly outside regions, but it's all the matter that is around the black hole, not in the black hole itself. I hope that helped.
Thank you very much. Yes, Liam.
Are you dealing in the entirety of your work collected, create wonderful animations and everything you've done? Just curious, you had terrible.
The question is essentially, how much data have you collected to be able to produce these various images and animations and so on? Is it measured in terabytes or well beyond?
Maybe up to a terabyte. It's not much more beyond. It's a lot of images, but they're not necessarily extremely heavy. So yeah, maybe a terabyte or maybe a few terabytes at most, not more than that, I think. But it's 30 years. It's gonna be the 30th anniversary of the Galactic Center Group this September. So it's been 30 years that we collect imaging data. Spectroscopy came in a little later, around 2007, I think, or 8. But it's been 30 years that we have been collecting data, and we observe typically 10 nights per year. And each year we observe at each night for about 6 hours. So of course, not all the time a telescope is usable. Sometimes there are clouds, sometimes you're weathered out, sometimes the correction is not great, something doesn't work. It's a complicated machinery, but it's a lot of data, a lot of nights of observing, lots of hours put together. And that's the beauty of this, because we are obsessed about just one specific region, but it's extremely rich and very interesting. And it's one of the rare cases in astronomy where you actually see stuff happening in real time. Here you see something changing within a few minutes, which is pretty impressive. And you see stars moving on the time scales of just 1 year, because everything is so extreme and moving so far in this region. So it's a lot of fun.
Happy birthday coming up for your group. Yeah. Any others before I turn it back to Raisa? I think we're ready for whatever else is on your side, Raisa.
Sure. So let me ask the last question before we adjourn. So the questioner wants to know, you did talk about the age of these objects and some paradox of having the younger ones closer. So do we have a general trend in these objects? So do we have generally, besides the exceptions, the older ones closer to the black hole and then the younger ones further away? Or is that not just true?
Unfortunately, that's what we expected, but it's not what we observed. So there is most of the stars are old, but the luminosity of the region is dominated by young, massive stars, and they are very close to the black hole, as close as the old ones. So it's not a concentric view where you have the old ones and then the younger ones around. That's what we would have expected, but it's not what it looks like at all. So we have it's basically three populations: a very old one, a young one, and a slightly less young one, but still young, too young to have been formed far away and then migrated inward. So that's what we observed, and there are some theories and models on how you would create that, but it's called the paradox of youth, because you're not supposed to observe stars this close to a black hole. So it's definitely against what we would have expected as a trend.
Okay, great. Thank you very much for a wonderful talk. And I would like to also thank our audience for being with us. And I wish everybody a great night. And bye-bye, everybody.
Thank you very much. Good night.